Welcome, everybody. I know I stand between you and a reception and drinks, but I hope you enjoy this anyway. I'm Brendan Burns. I'm an engineer at Microsoft Azure. I'm responsible for a lot of the container work that we do. I'm also one of the co-founders of the Kubernetes project, so I've done a lot of work on open source containers as well. And today I'm going to talk a little bit about how you can modernize application delivery with containers in Kubernetes. And so I'd like to start out by asking a question, which is, why do you care about containers? Right? And then another one, which is, why do you care about orchestrators? Kubernetes is a container orchestrator. And to sort of complete the buzzword bingo, why do you care about microservices? Why do you care about all of these sort of hype words that have been in the lexicon for the last 3 years or so? They've increased in popularity. A lot of people talking about them, a lot of conference titles, a lot of people attending things like this. Why should you care? Well, I'd like to posit that you don't. Right? Or at least that you shouldn't. And if the only reason you're here is because containers was in the title, or because Kubernetes was in the title, or because you really wanted to learn about the latest in microservices, that's the wrong motivation. So if that's the case, what do you care about? Right? What are the things that you care about? Well, I would posit that you care about your product. Right? We're all building something. We would like it to be useful to people. We would like it to make people's lives easier. We would like it to enable things that they might not otherwise be able to do. We generally want to build something that is useful to a group of people. We care a lot about our product. Likewise, we care about our users. Right? We want them to have a good experience. You can have very useful tools that are very hard to use. It's much nicer if you have very useful tools that are easier to use. So we can care a lot about how well our product works, but we would also like to talk about how easy it is to learn about, how easy it is to orient to. We care about our users. We care about our SRE, our site reliability engineers, or operators, or DevOps professionals, or whatever the term is we'd like to refer to, the people who keep the software up and running, who keep it patched, who keep it upgraded, who ensure that as a developer lands a piece of software, it becomes something that is safely and securely rolled out to production. Because ultimately, if these people do their jobs right, the product is awesome and the users don't notice. But it's important that we care about them as well. It's important that they have an easy life rolling out the software, ensuring that it's reliable, ensuring that if they need to roll back a version, that that's easy to do. I would posit likewise that you care about your teams. You care about the people who are building the software, who are designing the software. You want them to be able to move agilely. You don't want them to have to go through a 20-item checklist just to make a single change. You don't want them to have to coordinate, especially across a large organization, with 2, 3, 4, 10 different teams in order to roll out a feature into production. We care about our team's agility. We care about our team's ability to experiment. Ultimately, all of these abilities take you to a better product and a better user experience. But honestly, we care about that team's happiness. And so if these are the things you care about, your product, your users, your operators, your teams, what do containers have to do with it? Right? Because I will say, actually, I think you should, if you care about your teams, you should care about containers. And if you care about your product, then you should care about orchestration. And so for the rest of this talk, hopefully I'm going to be trying to tell you what containers have to do with the things that you actually should be caring about. But I wanted to start with the middle there, which is the container. So what really is a container? Because I think it's a word that has become very popularized and sort of hyped up and, again, is in a lot of conference titles. But it means a lot of different things to a lot of different people. So just as a show of hands, from people who sort of first heard the term containers 3 years ago? How about 2 years ago? 1 year ago? OK. So a while ago, people started hearing this. How many people are using containers in production? So few people. Right? So I think we're on this trend where the word has sort of entered the lexicon. It means a lot of things to a lot of people, but not necessarily a lot of people have deep operational experience with it. And in many cases, that operational experience varies. So what do really we mean when we say a container? Well, the first and most important, maybe not most important, but the first reason that most people came to containers was this problem that you see illustrated here. Oftentimes, when we're deploying 2 different applications onto the same operating system, onto the same machine, they may share a library. And this introduces this coupling, this tying of the two applications together, such that if you ever want to upgrade that shared library, you have to upgrade it for both applications. Now, it could be that application 1 really wants a new version of that library, but application 2, that introduces a bug for their application, and suddenly you're stuck. Or even worse, application 1 is suffering from a bug. They want to upgrade the library. Application 2 will have a bug if you upgrade the library, so you have to wait around for maybe a new version to appear. This sort of shared dependency makes it very difficult to roll out software, makes it very difficult to understand possibly the impact of rolling out software. And so one of the very first things that a container did was it said, actually, this sharing is a bad idea, right? Let's actually go and take a version of the shared library and put it inside the container itself. With the container image, we have this packaging and deployment mechanism that allows us to sort of hermetically seal everything that we need for the application, put it inside of a nice clean box, get it out of the operating system, and hand that thing around, right? So we can say, OK, I don't actually care what you have installed on your operating system. When I install a container, it's going to have everything that it needs to operate successfully. And likewise, I don't have to care what other applications might be installed on that operating system. They'll have their dependencies packaged up with them, and I know that we'll live in separate spaces where we don't interfere with each other. This solving of the sort of DLL hell problem is, I think, really one of the very first reasons that people came to containers. Now, one of the other values of having all of your dependencies packaged up like this is it also eliminates the need for scripts. It eliminates, because everything comes inside this image, it eliminates the need for running a script on the machine to do anything other than install this image. And because every image lives in its own space, if an image fails to install, you can simply try again. And the new installation of that image is not going to have any problems due to any residue left over by the previous installation of that image. It's this hermetically sealed, completely idempotent unit of deployment that really solves a lot of the sort of reliability issues that people see when they're moving from running things on individual machines under their desk to running things at larger scale inside the cloud. But this packaging and deployment mechanism isn't the only reason that people were interested in containers. One of the other main reasons is when Docker created the container image, they also created the idea of a container repository and what the value and a container registry. And the value of this is it actually tells you how you can distribute your application to the world. So at this point, a container registry is a core feature in every public cloud that exists. Azure has one, the Azure Container Registry. And what this means is I can do my development on my laptop. I can build an image on my laptop. I can push that image to the registry. And then I can pull that image across the world to virtual machines, to physical machines. It doesn't matter. I have a way of distributing this hermetically sealed application package that my developers have produced. Now, obviously, probably if you're further along in the development cycle, you actually don't want your developers to be producing that image. So you can substitute the laptop dev there for a CI/CD system. But the same things are true. You can use a CI/CD system like Jenkins or VSTS to build up your container image, and then use this registry to deploy it out into the world. So we've solved not just the packaging problem, but actually the distribution problem as well. And by standardizing on these interfaces, standardizing on these APIs, we've reduced the burden on your teams to figure out what's the right solution and how should I administer it. Because again, these things are all cloud services that you can consume software as a service. All right. So that's not the only value, though, the packaging and the distribution of these packages. One of the other real values is that simply the act of introducing a boundary forced people to think about organizing their stuff, right? When you think about an operating system, you think about a traditional virtual machine, there's all kinds of different stuff. You don't really know where it came from. Maybe somebody logged in and downloaded something from the internet. Maybe somebody ran a script. Maybe it was left over from a previous installation of something. It's very hard to know where things came from and what team was responsible for it. So you may need to free up space on a machine. You've got no idea really necessarily why this file is here or what application it might be attached to. With a container, because it gives you that boundary around all of the dependencies of the application, you have a clear boundary for your stuff. And that says, OK, we know very certainly all of that stuff is associated with this application that is associated with this team. We know where it came from. It's a separation of responsibility. right? So that you can have a team that's responsible for a web server be independent from a team that's responsible for a login daemon, that's independent from a team that's responsible for monitoring. They can all be distributed as separate container images. Nobody has to really coordinate to get these things onto the machine. It really provides a lot of decoupling, and we'll see why that's valuable for your team's agility later on. Additionally, I would argue that the very act of drawing out a boundary, the very act of saying, like, hey, there's this thing that provides a separation between your stuff and your not stuff, makes people think more clearly about what the right stuff to have in there is. So just like I think classes in object-oriented programming tell us there is, when you define a class, you think a lot about, like, what does this class mean? What is the core components of it? Likewise, when you declare one of these containers and you start putting things into it, you start actually breaking your stuff up into more reusable, more modular, more sort of purpose-aligned units. That act of organization alone is useful, independent of the fact that you can now have different teams running the different pieces of what ends up on your operating system. And then finally, and somewhat ironically, the last piece of container is runtime isolation. I say ironically because actually this was the primary motivation for much of the container technology that exists in the operating systems. The primary motivation was, I have two applications, my production web server and my intern's Minecraft server. They're running on the same machine. I want to make darn certain that that Minecraft server can't interfere in terms of using the CPU or using memory with that production web server. And so at the kernel, at the operating system layer, a container allows you to isolate two processes from one another in terms of the resources that they consume and ensure that if your web server needs 4 cores, it gets 4 cores for sure, and no matter what that Minecraft server happens to be doing. This is really, I think, the last reason that people came to containers, actually, in this sort of resurgence of container technology, despite being the original motivation for much of the work inside of the kernel. And the reason is because in this world of cloud and in this world of reliable application deployment, honestly, the packaging and deployment management problem was much, much more pain than the fact that you could drive utilization on your machine really, really high if you can have this kind of resource isolation. Now, ultimately, at a large scale, the ability to land multiple applications onto a machine and have them not compete for resources really can dramatically increase your utilization of machine from sort of an industry average of 10 to 15% to closer to 60 to 80% of the machine in active use at any time. Obviously, that's a dramatic savings on either your power bill or your cloud infrastructure bill if you can achieve it. And we'll see how orchestration can help with this. It's important to point out when I talk about runtime isolation that this is not security isolation, right? This is about isolating you in terms of the memory, in terms of the CPU. It's not about keeping out malicious users. At this point, a hypervisor is still the only security layer that you should trust for isolating two different workloads that may be hostile to one another. And so actually, there's a lot of work happening inside of Windows to have not just Windows containers, but Windows Hyper-V containers, so that you can have that Hyper-V level of security, as well as the runtime isolation, as well as the sort of packaging and dependency isolation that the container image provides. OK. So while we've talked a lot about the value of the container, I haven't talked very much about the cloud. And so the question is, if I have this container, which is a runnable thingy, which has this play button that I can press to run the container, it's an abstraction. I don't really care what's inside the container. I know that I can start it up. I don't care whether it's C# or Java or Node or Go or whatever. Somehow I know there's something that I should run inside there. How does the cloud fit into this? Well, the very first way that the cloud fits into this is something that we announced at Build last May, which is Azure Container Instances. So Azure Container Instances, the name that I called it when we were developing it was actually Container IaaS. It's really intended to be the equivalent of a low-level virtual machine. And it provides you just that ability to run a set of containers together on the same resource. But the value of it is you don't think about machines anymore. In fact, the machine is gone. You can't see the machine. All you see is the container, and you walk up and you say, here's my container image. It needs 2 cores and 4 gigs of RAM. Please go run it somewhere on your cloud. Right? Everything that you thought about in terms of operating systems is gone. You've focused entirely on the application. All right. To give you an example of how this works, I want to do a brief demo of Azure Container Instances. So we'll jump on over here if this works correctly. I'm vaguely blinded by these 2 lights here, so I'm now having trouble seeing my screen. But All right, so let's take a look. Here's a simple Node.js application, a really simple JavaScript application that serves a web page that says hello Ignite. So you can see that right here, simple web page. If all goes well, it won't have errors, but if an error happens, it'll say something bad happened. This is my application that I'm going to package into a container. All right, so here's a Docker file. I don't know how many of you have played around with Docker, but Docker allows you to have sort of a make file, a specification for how to build your container. It's the Docker file. In this particular case, I'm going to say, I'm going to start with a node image. It's going to expose port 80. I'm going to copy my source file into that container image. And then the command that I want to run when the image is run, that press play button, is node and my JavaScript file. All right. So let's build that. So I've built that container image, and I built it previously. That's why it's so quick. If you're building it for the first time, Docker caches a lot of things. So if you're building it for the first time, it'll take a little bit longer. But trust me, it just built all the way through it. I'm going to push that up to the registry. And so now I'm actually taking it from my local machine, pushing it up into the registry. Again, it's been pushed before, so they all exist, so it's quite quick. And now I'm going to actually deploy this application to Azure container instances. And so I'm using the AZ command line. I'm giving it that image that I just built and pushed, a resource group. I'm asking it for a public IP address. And then once it finishes doing the deployment, it will print back out that it's available. And there you go. The container is up and running in Azure now. It's running on this public IP address that you see here. And so I've taken that code, packaged it in a container, pushed it out to a registry, and deployed it to Azure. And at this point, I'm going to cross my fingers that this actually is still serving, but we'll see. It's going to wait for the container to come up all the way and the load balancer to get connected up. Fingers crossed. And there we go. The server is running, and I can curl it. I can see that that server is running. So in the span of 10 or 15 seconds there, I've gone from the container image on my laptop to the container image running on a public IP address in Azure. If my application fails, it gets restarted. If the underlying infrastructure that it's running on fails, the container moves. And so you have a very reliable application-oriented primitive that can run whatever you want, because as long as you can put it in a container, you can run it in Azure. And I'm really excited that here at Ignite, we're announcing that this is available not just for Linux containers, but for Windows containers as well. So you can package, whether it's a Linux application, a Windows application, you can package it and run it via Azure container instances. So I'll go back. All right. But oftentimes, you want more than a single container, right? Very few applications are simple enough that they fit inside of a single container. Azure Container Instances is really about individual containers. But many times you want an orchestrator. But once we start thinking about building up related services and services that work together, we are introducing a lot more complexity into the system. We're introducing a lot more ways that things can fail. And that's really where Kubernetes comes in. This image has been in like practically every talk I've ever given, and so if you've seen one of my talks before, you've seen this image before. But the real thing is that it crystallizes for me is that the challenge of driving something like a semi-truck is the fact that you have this two-dimensional system with this coupling in the middle. And movement in one place is not correlated to movement in another place, and that's ultimately what causes this truck to jackknife like this. And in fact, in my experience, when we go about deploying software, I find that most outages are self-inflicted. They're not self-inflicted because we think, hey, I'm going to wake up this morning and deploy bad software. They're self-inflicted because we have this coupling that we don't understand and doesn't make sense. So if you imagine backing up a tractor trailer or backing up a boat, if you've ever tried to back a boat down a boat ramp, backing up in one direction pushes the trailer in a different direction because of that coupling, because of that hinge point between the two systems. It introduces this complexity that is harder for us to reason about, that doesn't always make sense. And if we don't know that the coupling is there, we make changes in one part of the system that ripple to another part of the system and cause an outage. And in my experience, that's generally how outages happen. So in fact, I think that this job of operating software is too hard, and we need to eliminate the coupling wherever we can, right? And so what I want to show you now is how containers and container orchestration can eliminate the coupling between the systems and allow you to have teams that move and operate independently. And this, in fact, allows us to decouple the task of reliability engineering. We can actually say, you know what? If I'm using Azure IaaS, hardware SRE is taken care of, right? I've abstracted to Azure taking care of racks and taking care of network switches. When I start thinking about containers, I've actually separated out application from operating system. And so I've actually decoupled the people who manage my operating systems from the people who manage my containers. Now, in order to actually use containers at scale, I need a piece of software, the cluster orchestrator, that manages a lot of machines. But fortunately, that's an API too. I can actually decouple myself from that as well and say I'm going to provide container orchestration as a separate layer, as a separate API. And then my application developers can simply consume clusters and container orchestration as the primitive that they know about. And in this way, I've decoupled all of my teams from one another. They can each move independently. Azure can, remove racks of hardware, and you don't notice, hopefully. Your operating system people can upgrade and roll out new versions of the operating system. Your container is isolated from that. The cluster administrators can focus on delivering a reliable cluster orchestration API. And indeed, if you use Azure Container Services, Azure itself will help you deliver that reliable container API. And your application developers can think in terms of container images and the containers that they want to deploy, not any of the details below. And so this sort of decoupling really makes life a lot easier. And I think, in fact, application SRE is really what people meant when they said DevOps. Right? DevOps was sort of a catchphrase for a long time that I think meant we want our developers to help hold the pager. I don't think it ever really meant we want our developers to update the operating system. But until the advent of container technology, the decoupling of the application from the operating system simply wasn't possible. And so DevOps came to mean people, developers, operating the whole stack, which is inevitably a bad idea. Likewise, actually, it turns out running the cluster is actually a DevOps operation as well, because the cluster is just a specific instance of a particular application. And as I mentioned, we can offshore the hardware with Azure Virtual Machines. Container images allow us to decouple the kernel. Kubernetes and Azure Container Services allows you to decouple the container cluster manager. And then, obviously, still you have something left, and that's application management and application deployment. But this is sort of the operator's view of the stack, the operator's view of the decoupling. From an application developer or a DevOps view, it actually looks more like this. I've got a homogeneous fleet of machines. I've got this cluster orchestration API, and I've got a bunch of containers. And it turns out that this line, the container API line, becomes the not my monkey, not my circus line. Right? So this becomes the place where your people who are focused on application development and application deployment trust that the container API is there and is useful. People who are focused on operating systems focus on delivering the operating systems and the cluster containment API. And effectively, we've separated ourselves. We've have difference of responsibilities. We have isolation of our responsibilities. And we can each live our independent lives and focus on the things that matter to us. It's hugely empowering for the different teams. But of course, even with this, it can become complicated to deploy one of these container APIs. And so I wanted to show via slideware, effectively, because it's actually not that exciting, how you create an Azure Container Service that can be that abstraction API. So this is really all it takes to create an Azure Container Service. You create a resource group. You may already have a resource group. You create a cluster, and then you get the credentials for that cluster. Right? And so at this point, you've deployed a container. You've deployed Kubernetes, a cluster orchestrator, across a fleet of hundreds of machines, potentially. You have that API surface area that you can hand out to your developers, and you have Azure helping you manage the rest of the infrastructure. Right? And I think that this notion of management and this notion of automated healing and all this sort of thing is hugely valuable for people to think about, because as we start thinking about how we can deliver reliable applications at scale with high agility, we can't do it all ourselves. The analogy that I like to draw is a long, long time ago, I built a balsa wood model remote control plane. It took a long time. I was a kid. And it took a long time to build this thing. And I was really excited. I took it down to the park. And I fired it up. And it flew. And it went up. And it went down. And the balsa wood, if you've ever built a balsa wood, it just exploded. Right? So like months building this thing, 15 minutes before it was destroyed. Right? More recently, I've given my kids a quadcopter. Right? And my quadcopter and my phone and my 5-year-old is driving a drone around our house, right? So it's this radical change in kids' experience of flying vehicles, right? And it's not a non sequitur. It's actually because that quadcopter is self-balancing. That quadcopter is running a piece of software on top of it whose job it is to take intent and turn it into action. So that when my son says, please go forward, there's a piece of software that is autonomous and running on that quadcopter that moves it forward. That was never present on that remote control airplane that I had. And as we move towards cluster orchestration, what you're going to find is the same thing is true. There's control software running inside of that cluster orchestration system to make the job of developing, deploying, and managing reliable software easier. So it's not just about decoupling everything so that we don't interfere with each other. It's actually about taking the task and making it simpler by adding automation and online automation into the system. So to give you an example of this, consider the task of keeping a container up reliably. I might have 3 nodes, and I have 1 container that I want to run. Well, if that container dies, Kubernetes will restart it for me. It will see that the container is dead. It will see that the container is hung even, and it will kill it and restart it. Right? What if the machine dies? Well, if the machine dies, Kubernetes notices that the machine has died, and it actually moves the container from one machine to another machine, still up and available. I still haven't been woken up, right? As an operator, I'm still asleep in my bed. I know no difference. My users know no difference, because this autonomous system, this autonomic system, is responsible for ensuring that my intent, which is that my application was running, is matched with reality. It's a much simpler world. But of course, in reality, we actually don't want just 1 copy of this. We actually want multiple copies. And so actually systems, Kubernetes and other orchestrators actually make the task of replication easier as well. So I can express not just that my intent is that this thing is running, but my intent is that 3 of this thing are running. And the system will be responsible for that. If I want to scale up, I simply say, my intent is that 4 of them are running. And 4 of them start running. Right? To give you an illustration of this, I want to do a quick demonstration of deployments via Kubernetes. So we'll go back over to the demo over here. All right. So what I have here is a simple service. This is a load balancer that's responsible for load balancing traffic to, is that large enough? I should have asked before. But is that, can people see? Yeah? OK. So what, in Kubernetes world, it's called a service. It's a load balancer, basically, for a replicated series of containers. It's actually not really that interesting, other than it's serving on port 80. And it has this selector, which indicates the things that it wants to load balance traffic to. So rather than giving an explicit set of things, because these things can die and move and scale and things like that, I say, this is the class of thing that I want my traffic to be load balanced to. Likewise, so here I'm going to go and create a namespace, which is basically, you can think of a namespace as a folder. It's like a way of organizing my stuff. So it's a folder that'll keep me. It's not for security, really. It's more just to keep my stuff in separate, organized places. And I can deploy v1 of my application. This is a deployment, which is represents the idea of deploying a particular instance of the software. It's not super interesting. There's a few things to look at. One is that it says right here, I want to have 5 replicas. So that's my assertion that I want 5 of this thing. And then over here, I have 2 containers. One container is actually just writing v1 into a simple HTML file. And the other is running the Nginx web server to serve it. So in Kubernetes, you actually can run multiple containers joined together, actually ACI as well. You can run multiple containers that are sort of joined together and symbiotic. Remember I said one of the values of containers is this modularization? These 2, they each have their own jobs. The Nginx's job is to serve a web page. The other script's job is to basically keep that web page up to date. In this case, just writing v1 into that web page. And so separation of concerns, but working together to deliver a reliable service. And so I'm actually going to go and deploy this into the Kubernetes. Now it's actually been deployed. 5 of those replicas are out there. And what you see there, down here, is there are those 5 replicas up and running. What's going on in the middle is I'm actually going to start putting load onto the system. And so you can see it's moving through different host names. It's printing the host name and the version of the software that it's running. Since there's 5 replicas, it's going to round robin through those 5 replicas that are up and running. And now actually what's going to happen, but they're all serving v1, so the v1 stays the same. What's going to happen now is I'm going to actually update the deployment. I'm going to replace v1 with v2. Right? And I'm going to deploy that. And so now over on the right-hand side, what you see here is I've asserted to Kubernetes that I would like the deployment to be v2. And it's doing a rolling update from v1 to v2. Now what's important to note is as I put traffic onto this, you're going to see v2s starting to show up. What's also important to note is you're not going to see any errors. Right? So I'm actually taking down containers, killing containers, starting new containers. But because I have health monitoring and I understand the health of the service, I'm never going to serve traffic onto a container that's not ready to have traffic. And so I'm never going to have any errors as I switch from v1 to v2 of the service, because the autonomic system understands whether or not the place where it might send the traffic is healthy or not. Right? And so now at this point, I've done a complete rollout from v1 of my software to v2 of my software. But let's say I don't really like v2. Right? It's not a great system anymore, it turns out. I want to roll that back. Well, actually, all I have to say is, like, I want to do an undo of that deployment. Right? And at this point, you'll see that actually a rollback is just a deployment in reverse. And so I'd wanted 5 replicas of v2. Now I've said I want 5 replicas of v1. And it's slowly scaling back from v2 to v1. And as you can see over there, new host names are showing up. v1 is starting to intermingle into the v2 load that I have. And eventually, in just a second, I'm going to be back to my initial state of having 5 replicas of my version 1 server running, no replicas of version 2. Right? So in the span of 20, 30 seconds right here, I have rolled out one version of my software, rolled forward to a new version of my software, decided I didn't like it, and rolled back to an old version of my software, all without any user noticing. Right? And that's hugely powerful. And again, it's because the system is autonomously responsible for taking care of making sure that your intent matches reality. So we'll drop out of this demo eventually. All right. All right. Back into the presentation. All right. So, but then if we have this, then I would say at this point, containers and container orchestration are an expected part of every public cloud. Right? Every single public cloud that exists has a container orchestrator that you can deploy into it. And so this is just an accepted part of the cloud landscape. How is this transforming how we build our applications? Well, one of the most radical things that it's transforming, I think, is the platform as a service landscape. Right? So it used to be traditionally that platform as a service went all the way down to the bare metal. Right? If you wanted to deploy an application into functions as a service or anything else like that, it goes all the way down. It manages not just the user interface to that system, but actually all the way down to the machines. And so therefore, choosing a platform as a service was a big architectural choice. What we're seeing is platform as a service is being replatformed on top of container orchestration. And so your choice can be, I want to adopt a container orchestrator. Platform as a service can be one vertical that is installed on top of that container orchestrator. It's a much lighter weight choice. And because it's a lighter weight choice, you can afford to have multiple of these platforms. Even different teams can choose different platforms that suit their particular application needs. Right? So this is hugely empowering, not just because it's easier and quicker to build platform as a service, but it's actually enabling the choice of platform to be made by individual teams, not overall large organizations. Again, reducing the amount of coupling that happens between your teams, increasing their agility, increasing their ability to deploy. And so in particular, when you think about this, there are things like Deus Workflow, which Deus is a company that Microsoft purchased about 6 months ago that does a lot of container work. They created a Heroku-style PaaS. So if you like the Heroku workflow, you can install Deus Workflow on top of your Kubernetes cluster, have a Heroku-style experience. Right next to it, you can go and install this thing called Kubeless. Kubeless is an open source project not associated with Microsoft, although we use it. It implements functions as a service on top of containers and on top of Kubernetes. Right? So I can have a Heroku workflow next to a functions as a service workflow. Deus also has this thing called Helm that is like Chocolatey or Yum or any of these package managers that you may be used to on individual machines. But it's for your cluster. So you can use Helm to install applications onto your cluster and do package management on your cluster. Again, running next to your Heroku-style workflow, your functions as a service, all on top of this container orchestration layer. Spark, which is a big data platform, is in the midst of figuring out how they can run on top of Kubernetes as well. And so you can run your big data workloads next to your packages, next to your functions as a service, next to your Heroku-style workflow, all on the same container orchestration layer. Again, working together on the same machines, driving up the efficiency of each individual machine, allowing developers to find the place that fits for them. And likewise, of course, the raw Kubernetes API is still there as well. And so you can still deploy raw containers to the raw APIs if your application requires that degree of flexibility, or there isn't a platform that's well suited to you. Sort of to illustrate how this works, I wanted to give you a demo of Helm. So if I drop out, go back over here, get the Action Center to go away. All right, so here I am installing Helm onto my cluster. Helm has both a client-side component as well as a server-side component, or a cluster-side component. The cluster-side component is responsible for managing the various infrastructure. I can actually say, I want to do a search. Let's see what kind of MySQL I have. Just like any other good package manager, I want to be able to discover the packages that are available to me. I search for MySQL. I see a version of MySQL. I see Percona, which is a scalable MySQL. I see MariaDB. And so I now have the ability to deploy these packages. You can see that they each have a version. And what Helm supplies is not just the package management, but actually the version upgrading story as well, just like any other good package manager would do. Of course, instead of installing it onto any individual machine, it's installing it onto this cluster orchestration environment. So let's say I want to install MySQL. Oh, that's not good. It should be stable MySQL. Sure. How's that? Is that good? Keep going. Keep going. Let me know. Is this like the eye doctor? All right, cool. All right, so I can actually say Helm install. I have to actually type now, which is sad. Stable MySQL. And so what this is actually doing is it's actually going and finding the chart, and it's going to go and figure out all the different resources that need to be deployed, gives it a cute name, and deploys all those resources out to the cluster, and then gives you some information, right? Here I deployed this service, here's the deployment. We talked about deployments that represents it. And then it says, oh, and I created this secret that has your password in it if you want to access it, right? And so at this point, I've deployed a reliable MySQL out into my cluster. It's actually configured secure by default so that I don't have, MySQL as the password or even blank password, which is even worse. It's running on a persistent volume, an Azure volume, so that if my container moves between different machines, the database is still there. It moves with the container. So at this point, I can use this package manager to install all sorts of different off-the-shelf software. Likewise, I wanted to actually, and I don't even really need to jump back to my deck, I wanted to give you an illustration of running functions as a service on top of this container orchestration layer. And so I can actually show you kubeless running. So I'm first going to create a namespace, that folder to hold everything. And now I'm actually going to curl from the kubeless release site up on GitHub through to create the resources. And what you can see here is to install this particular piece of software, it's actually installed Kafka, which is, you may have seen, it's a queuing system. It's installed Zookeeper, Lock Server. It's created a controller which provides the API. It's created a bunch of service load balancers. Again, it's assuming that the cluster orchestration layer is there and it can be used to deploy itself, not anything that you need to know about. What's especially interesting about this functions as a service is it's actually created a third-party resource. So before I had installed any of this software, Kubernetes knew nothing about functions as a service. But because the Kubernetes API server can be extended to add new API types, it's actually now knows about this idea of a thing called a function, right? There are no particular functions deployed right now, but I have the ability, the system understands them right now because I've extended it with this plugin. So here's a simple Python function. It just prints hello and the message that came in. I'm going to deploy this out into that functions as a service runtime using the tools that are provided. So at this point, I've deployed that little Python function in functions as a service style out into the service. It's actually been packaged as a container, deployed out to the orchestrator, but you don't know that or even really have to care about that because this platform has provided the functions as a service interface for you. And then if I get my functions now, you can see that I've actually declared a new function. And so the Kubernetes API knows about this function that has been defined. And then I can actually make a call to it, pass in ignite demo, and it actually has then gone and made a call out to my functions as a service with this value as the input, gotten the message back. And then, of course, I can delete the function as well, and if I can delete the whole thing. And now I've actually, in the space of the time that we've just been here, I've installed functions as a service, deployed a simple function, accessed it, deleted the entire functions as a service platform from my container orchestration cluster, right? So these things are becoming modular, lightweight choices you can experiment with, find the one that works. As operators of the cluster, I don't even know what you've done with it necessarily, and that's OK, right? So that was the extent of the functions as a service demo. I want to jump right back in. And I think I'm not going to have time to do my last demo, but that's all right. All right, cool. And then talk about, so this is all stuff that we can do right now. I think what's even more interesting is that how this cluster orchestration plugin model is being extended to add new capabilities, right? So we can deploy these platforms, and we're very used to using these sorts of platforms. But what we're actually seeing is people starting to add modularity and daemons to their cluster. We're very used to the idea of agents or daemons running on individual virtual machines. What we're starting to see is people are running agents or daemons on the cluster environment itself. And in particular, there's this one great example, I think, which is this thing called kubelego. Kubelego is a daemon that you can deploy into your cluster that uses Let's Encrypt. Let's Encrypt is a service that will give you an SSL cert via an API. So it used to be that getting a certificate and getting it deployed out was a fairly involved, usually very manual activity. With Let's Encrypt and this cluster daemon, I just need to add an annotation to my service, to my web service that is running, the load balancer that's responsible for my web service. The daemon itself, so it's introspecting the services. It sees that I've added this annotation that I want a service and the host name that it's responsible for, and it actually is responsible for going and getting the certificate and injecting it into the load balancer all automatically. So what used to be a manual process of finding a cert, downloading the cert, associating it with an image or associating it with a machine becomes a text annotation that I've put in my declarative configuration of the application that I want to deploy. And I have actually 2 minutes. And you can actually obviously do this for multiple of these services. It's not limited to any one service. Any service that you deploy into Kubernetes, you can apply this to. And I have 2 minutes left, and so I will jump into that demo as well. This demo actually totally failed on me yesterday. And so I'm going to hope that it works today. But we'll see. It actually worked, but it took like 10 minutes for Let's Encrypt to respond. And so you were all gone by the time that it worked. But trust me, it worked, though. No, really, honestly. All right. Let's see if it's a little faster today. All right. So I'm going to use Helm again to install kubelego. Kubelego has a bunch of parameters. Helm is a templating engine, so you can parameterize it, so you can customize it on the fly. I'm going to curl my little demos here, and you're going to see it's got a bad certificate. Curl has said, hey, certificate validation failed. I don't understand what you're talking about. I'm going to deploy kubelego into my cluster. So Helm install, I'm going to use Helm install to deploy that into my cluster. Now that daemon is up and running, and it's actually given me a really handy sort of what to do now. And it says, OK, if you take your service and you annotate it with this annotation, and you have a host name down here like this, we'll actually go get a certificate for you and associate it with your service. So let's actually do that. I've got my service here. In this particular case, the host name is demos.azurecontainers.io. I've added this little, I would like to have a certificate associated with this. And I'm going to apply this to my container cluster. It's reconfigured it. And at this point, you can see that curl, see, it worked actually this time. That curl, which previously had a certificate problem, the exact same curl now gets the Nginx homepage, right? So the simple act of adding a little textual annotation to my HTTP load balancer has associated the certificate with that host name, with my service, automatically for me. This is, again, not just about making it easy, but actually about decoupling responsibility so that the people who are responsible for SSL certs and management can deploy this daemon. It doesn't have to be Let's Encrypt. You can deploy your own cluster-level daemon. Every user of that cluster can then have access to reliable automatic certificates without any intervention on their part, without any mistakes that they might make. So I hope that that gives you an illustration about how container orchestration and decoupling all these applications can really radically simplify and speed up your development environment. And that's the end of my talk. And I'm happy to take a few questions afterwards, assuming no one else is here to kick me off. So thank you so much for listening.